turns out to be 6. And so Jeff and I were able to show this. So A of n, if we call this A of n, A of n is a 6 regular sequence, meaning that there's some recurrences like the merge sort sequence, but instead of base 2, looking in base 6. Okay, so how do you prove something like this? Well, you can guess the recurrences that it satisfies, like I mentioned earlier. And so what you want to do is show that the conjectured sequence.
So you guess with the computer, of course.
Yeah, of course. Yeah. Well, we also, you don't want to continue to do this by hand. So So what we did was generated the first few thousand terms or more, I don't remember, and then guessed it. So we want to show that the conjecture sequence is 3/2 power free, and also is the lexicographically least such sequence. And the part of the proof that I want to talk about is this. So there are some details in the proof. It's not it's a proof, but it's not the most enlightening proof in that we don't have a sense of, if you gave me another fraction instead of 3/2, could I tell you whether the sequence is going to be k regular and what the value of k is? So we don't know. It looks like if you use 4/3 powers, for example, you get something similar, but it's not quite as nice. So we don't know. It's completely open in general what happens for other rational powers. And so what happens then? So we have a proof. The proof works like this. And I'm not going to talk about too many details of the proof, but I want to talk about this case, the showing that it's actually 3/2 power free. And I want to write down an expression that Jeff came up with.
But Eric,
Yeah.
to generate the data, of course, you use a computer.
Yes.
But to collect all these nice patterns, you did by hand?
No.
Also?
Oh no. So this was by hand, right?
Yeah.
So yeah, this was by hand.
So it'd be nice if computer.
It would be nice to even have So what this came down to was showing that some ugly expression. So then these C and D functions, or these other auxiliary functions, basically you have to show that if you have an infinite sequence and you think it's 3/2 power free, you have to show that every subword in the entire sequence is not a 3/2 power. Right? And so I'm not going to explain why this particular inequality shows it, but it does. What we want to show is that B of D of S m plus C of S is not equal to B of D of S m plus C of S plus 6S. So basically we're saying that, for all S at least 1 and m at least 0. So the claim is that if we show this inequality holds for every S and m, this shows that this conjectured sequence is 3/2 power free, and then you also have to show that it's lexicographically least, which means decrementing any letter, any entry is going to give you a 3/2 power. So what this is saying is we're sort of evaluating the sequence, this B column. We're evaluating this B sequence somewhere, and then 6S terms later, which is sort of corresponds to the length of the same subword that we're interested in showing is not a 3/2 power. We want to show that those letters don't line up so that we can't have a 3/2 power. So this was found by hand. Okay. So there are 30 cases. One for each. So breaking up m mod 6, we have 6 values of the last digit of m in base 6, and then S, so if we're evaluating C and D at S, and what does S depend on? It depends on the last non-zero digit. So C and D depend on the last non-zero digit of S, right? Because we have a bunch of zeros, and then we have either a 1, 2, 3, 4, or 5. And same thing with over here, if you can see it. So there's 30 cases, six possible values of M mod 6, and then 5 different values for the last non-zero digit of S. And so let's just write out case 1. So this is, let's say, M is 0 mod 6, and S divided by all the powers of 6 that it has in it is congruent to 1. So this is another way of saying the last non-zero digit of S in base 6, right? We're removing all the powers of 6 in S. So, you can imagine that it'd be pretty tedious to do this for all 30 cases. We did it for all 30 cases, but of course we didn't write all 30 cases in the paper. We only said, we wrote out the first 3, and then all the other cases follow similarly, and submitted the paper. And the referee said, well, you really need to give some more details about all these 30 cases. And so we could have spent an hour or so writing out all 30 cases, and then it would have been very boring to read. 2 pages of basically the exact same thing. But instead of spending an hour writing all these cases, I decided to spend several weeks instead writing a big program that would do it for me. And so that's where this all came from. So what the program does is it takes as input, in this case, as conditions, M equals 0 mod 6, and the last non-zero digit of S is 1 mod 6. And it outputs, magically, after several weeks of work. It also inputs this expression up here, so B of D of S M plus C of S is not equal to So these are the conditions, the assumptions that we're making.
So you have a data structure for this condition?
Yeah, I have a data structure for saying that it's basically this, just in formalized something. And for the last non-zero digit of S, I really write it like this: S divided by 6 to the nu sub 6 of S. It's congruent to 1 mod 6. And the output is following. So I'm going to try to distinguish between S's and 5's here. 2 nu sub 6 of S plus 5 if M is congruent to 0 mod 12. So mod 12 pops up instead of mod 6. And 2 nu sub 6 of S plus 6 if M is congruent to 0 mod 6 mod 12. And the right-hand side is 2 nu sub 6 of S plus 6 if M is 0 mod 12, and 2 nu sub 6 of S plus 5 if M is congruent to 0 mod 12. And so this is then what each case looks like in the paper. We have a bunch of these things which are succinct, just, this is what the left-hand side evaluates to, this is what the right-hand side evaluates to, and you can clearly, tell that they're not equal. Of course, I could also put it in the program to just say, well, if we have 2 piecewise expressions with the same conditions on both sides, we just compare them term by term. But then, of course, the program would just output true, and then we can't put true in the paper. And so this is the output.
So are all the outputs the same type?
Yeah, so it turns out that for this sort of thing, for this input, they're not always flipped. They're all of the form 2 nu of 6s plus something. The something changes there aren't always just two cases. Sometimes there's only one case on one side and two cases on the other side, and sometimes these conditions are a little bit more hairy. But it turns out that all the expressions basically look like this. So, so like I said at the beginning, this is sort of it's a hacky, messy program with a whole lot of notes to myself, like, oh, I need to make this better, and I need to make this better. And it was built to, specifically to solve this problem, which took a while to even do. What was I saying? Yeah. So, but in this case, they're all just fairly simple form.
That was actually helpful. Did Jeff or you also do it by hand?
So a year earlier, Jeff had done it by hand, and
But you didn't type
the
it?
notes, no,
Okay.
no, and the
So
notes
nice
were
typed.
the notes were somewhere, yeah.
Yeah.
And and it's just, I don't know. I had been kind of thinking about pushing in this direction for automate. It's case analysis, and no one likes to do case analysis, and it's not enlightening.
Yeah.
And there's no reason why we shouldn't be able to take an expression like this and just do routine things. Apply. So okay. So let me.
And Jeff may have cheated because somebody said that.
Well, I may have cheated also, but yeah.
Yeah.
It's possible. So let me just briefly tell you what the program does in very, very vague terms. So like I said, it inputs some expression and a set of assumptions about symbolic integers, symbols that are presumed to be integers, and then basically it just applies transformation rules and attempts to simplify them. So so what kind of transformation rules are there? Well, if we have mod of a plus b, comma k, then what it tries to do is, well, is this expression any simpler if we separate the two? So if we look at a mod k, can we do anything with that? And then can we do anything with b mod k? And if we can rewrite at least one of these terms, then it outputs, then it rewrites the expression. Similar things are like if we had use of 6 of 10 times 6 to the t, right? There's a simpler way of writing that, which is t plus the highest power of 6 that divides 10. Well, 6 doesn't divide 10 at all, so this is just 10. So the tricky part was was kind of coming up with a list of symbolic rules that'll always apply here. And so for this to work, of course, t has to be an integer, right? So we have to carry around all these assumptions about t being an integer, and then to evaluate this, we have to know that if t is an integer, then 6 to the t is an integer, and 10 times 6 to the t is an integer. So a lot of the details went into this stuff that I'm sure is built into Mathematica's and probably Naples also, general simplification algorithms. But I had to do some of it from scratch in order to be able to do some simplification that Mathematica and Maple can't do already. Let's see. So let me just end with one thing that I just found particularly interesting, which is that I mentioned that in traditional symbolic algebra, polynomials are sort of the basic thing that you work with all the time. And so it turns out that polynomials came up a fair amount in these computations. And so one general question is, if we have some polynomial, say as a univariate polynomial in N, and we want to sort of evaluate it mod K, what can we do? So what I mean is, we have some polynomial in N, and we want some simpler expression that we're not evaluating this polynomial at N, but we want an equivalent expression that's somehow simpler than this expression, where they agree.
So k here is an integer?
K here is an integer at least 2. Or, we could even say at least 1. But 1 is a little silly. And the polynomial is, say, integer valued. So, for example, 4n squared plus 2. All right, well, this polynomial is always even. So mod if we see this expression, we should be able to say, oh, well, this expression is 0 for any n. Well, okay, in this case, it's very easy to see, to write a program that will detect this, because we can reduce each coefficient mod 2. And when we reduce each coefficient mod 2, we get the 0 polynomial in here, and then 0 mod 2 is 0. So that's a simple case. A not so simple case where that doesn't work is this polynomial. Say mod 2 again. This polynomial is also always even, right? How can we see that? Well, we see that, well, if n is even, then this is even, and this is even, and this is even. If n is odd, then this is odd, and this is odd, so their sum is even. Right, so this polynomial is always even too, but this trick doesn't work. So what trick does work? If we instead don't use the ordinary power basis for polynomials, but instead use the basis of binomial, like symbolic binomial coefficients, then this sort of pulls out some extra stuff. So let me write what this polynomial is in binomial basis. So this is 2 times x choose 2 plus 4 times x choose 1 plus 2 times x choose 0. And hey, now look, all our coefficients are divisible by 2. And the reason this works is that we know that n choose I is always an integer. Right? So even though this by itself has a denominator, right? X choose 2 is x times x minus 1, 2, or x times x plus 1 over 2, one of the two. So that has a denominator of 2, but no matter what we plug in to x, if x is an integer, this is still an integer. So now we can reduce all the coefficients mod 2.
But that's just luck.
Well, is it? Yeah. So that's the question. What's given a polynomial and so a polynomial in x that's integer valued, say, and an integer, a modulus. Give me the polynomial or a polynomial with smallest degree that is congruent to the original polynomial mod k.
But to test that it's 0, it's a routine verification.
Well, yeah. You can plug in all residue classes. Yeah.
Yeah,
But what if it's not 0?
Right.
What if we had this?
Yeah.
Then
so you
this,
want to reduce it.
Yeah, we want to reduce it in general.
Because the 0 problem is routine.
Right. Yeah. We want to reduce it in general, not just test whether it's always 0. So I was actually, this is pretty good. I haven't actually found an example where reducing the binomial coefficients, mod k, does better than where it doesn't do as good as possible, if that made any sense. So the question is, can you do better? And I don't think it's a hard question, I just haven't thought about it that much. Can you do better than reducing the binomial coefficients? Coefficients in the binomial basis. And then, of course, the question is, if not, then what will do? Then what is the best thing you can do? All right. Maybe I'll stop there, and we have time for a few questions.
Thank you very much. This ends the official part of the talk, but I will be glad to answer questions in private. Thank you. And if you'd like to join us for dinner at 6:25 at